sound working? Yeah, that sounds good. Thank you. All right. Well, we are in the book of Isaiah, but I just wrote a book, Weathering Climate Change. I've heard that it's going to come out late March or April 1st, and I'm already working on my next two books, and one of those books is on interior designs. That'll probably be the title of the book. We're hoping to attract people who want to refurnish their homes and so forth. But really, it's going to all be about the interior designs of our super cluster of galaxies, the interior design of the Laniakea supercluster, the Virgo cluster, the local group, our Milky Way galaxy, our star, the sun, and then looking at the interior design of the Earth and the Moon. You kind of get the idea. And I'm developing several public talks I'll be giving on interior designs. And I got part of a talk developed that I want to test on you. One thing I always like to do with the Paradoxes class is to use you as guinea pigs, where I throw out the material that I'm developing for public audiences and get your feedback. And if you're not aware, this class is live streamed, and so we have a lot of live streamers that are participating with us here. And I'd appreciate any feedback you can give me about what I'm going to be saying in the next few minutes. And if I finish early, we're going to get back into Isaiah. But this also goes for those of you that are live streaming. You can text in your questions, your comments, and that would be quite helpful. And incidentally, the handouts we make in the class are all available at paradoxes.org. And we record every class. Every class is video recorded. And so they're archived at paradoxes.org. Incidentally, that's where we get the biggest participation in the class, are people that download the recordings. Now, I'm beginning here with this slide, and how many of you recognize this? What are we looking at here? Mars, okay. All of you work at JPL are well aware of this. And I chose this one because it shows you the North Polar ice cap. And you might be shocked that it's so much smaller than the polar ice cap on the Earth. And that's because, unlike Earth, Mars's rotation axis tilts back and forth by about 60 degrees. And when it does tilt over, that ice now becomes warm enough that it evaporates to outer space. And because of the air pressure on Mars being as low as it is, the freezing point of water is identical to the boiling point of water. And so whenever that polar ice cap gets tilted over, it quickly evaporates, but a new one forms. Just like planet Earth, Mars gets a fresh supply of water every day from bombarding comets. So there's actually an ice cap on the south pole of the moon, and it got there because comets deliver water. Comets are 85% frozen water, and so when the rotation axis stabilizes again, thanks to the comets coming in, you get a new ice cap that forms. But because it's only has a limited time to form, the polar ice cap isn't as big as it is on Earth. And by the way, that polar ice cap is not only frozen water, it also has frozen carbon dioxide. It's a combination of frozen carbon dioxide and frozen water. However, this was the subject of a research paper that was published just a couple of weeks ago in Geophysical Research Letters, basically demonstrating that the interior of Mars is nothing like the interior of the Earth. And this little cutaway here shows you what the interior of the Earth looks like. If you go to the very center, you've got a solid core of cobalt, nickel, and iron. And some of the models tell us that a good chunk of that is uranium, just because the models that we have to explain the heat flow through the Earth would require more uranium than we originally thought. And then outside of that solid inner core is a liquid core, also predominantly composed of iron, nickel, and cobalt. And those, of course, are ferrous metals, which means they're easily magnetized. And because it's liquid, the sloshing around sets up a magnetic field. So it explains why our planet Earth has a strong, long-lasting magnetic field. And outside that liquid core, you got the inner mantle, then the outer mantle, and then a layer called the asthenosphere, and then you got the crust of the Earth. And underneath oceans, you've got a thin basaltic crust, where you've got continents, you've got a thick silicate crust, and typically 4 to 6 times thicker than what you have underneath the oceans. And as you can see by this, we do have to scale the inner core, the outer core, and the inner mantle. Everything else is not to scale. That asthenosphere, for example, is very thin, but it's basically showing you that the asthenosphere is thin underneath the continents and quite thick underneath the ocean basalts. Now, the reason we have this distribution is because unlike the other planets in the solar system, there is strong internal heat flow from the core out to the surface. Explains why we got plate tectonics, explains why we got this strong magnetic field. And the experiment that was done on Mars just a couple of weeks ago was to look at this region of the North Polar ice cap, and they're able to measure the quantity of frozen carbon dioxide and frozen water there. And then they actually were able to use satellites that are going around Mars to try to measure the degree to which this weight of ice is pressing down on the crust below. And basically what they discovered is they couldn't measure any movement at all. Now, for example, the thousands of feet of ice that we have pressing down on Greenland actually push the crust of Greenland down into the mantle a little bit. You see that in Antarctica as well. In this case, they couldn't measure any movement at all. And basically what that told them is there simply isn't enough heat flow from the interior of Mars to set up a low viscosity mantle. I mean, the crust is solid and fairly rigid. Underneath the crust, we got this mantle, and a good way to think about it is like warm peanut butter. It's not liquid, but it has sufficient low viscosity that it's got some plasticity to it. And because of that, if you've got a lot of weight bearing down on the continent, it's going to push it into the mantle of the Earth by some measured degree. In the case of Mars, they couldn't measure any at all. And so they were able to determine that at maximum, the heat flow from the interior of Mars was no more than 7 milliwatts per square meter. So that's not going to warm your feet up very much if you're on the surface of Mars. Less than 7 millimeters. Say, how does that compare with the Earth? Well, on the continents, you get 92 milliwatts per square meter. Over the ocean area, it's about 67. And so that tells us that Earth has a much more powerful internal heat flow than Mars does. Now, I've written in my book, Improbable Planet, that the solar system planets are going to begin with a lot more internal heat than we see in other planetary systems. Why? It's because of the way our solar system formed. It formed in a fairly big open cluster of stars. They estimate at least 10,000 stars are in that cluster. And there were supernovae erupting. And so what happened was the emerging solar system got super endowed with uranium and thorium and other heavy elements. And uranium and thorium are radioactive. And so when the solar system planets formed, they had all of these radiogenic isotopes in them, which would cause them to have a lot more internal heat than what we would see in other planetary systems. And indeed, as you look at other planetary systems, we're not finding any evidence that they have any kind of long-lasting plate tectonics. What was different about the Earth, I mean, this is kind of where this paper went, basically making the point that if Mars had the same kind of history as the Earth, it should have a powerful internal heat flow. It doesn't. So what's so different about the Earth? Well, a few things we know that's different about the Earth is that it not only had all these radioactive elements when it was formed, and of course all planets when they accrete, basically planets form through planetesimals colliding into one another, sticking to one another, and growing and becoming a planet. But physics tells you that when you got a lot of material collapsing and accreting, you get increased heat. And so all planets begin with what they call primordial heat, heat that was generated by the formation of the body. However, with Earth, we know that there was additional accretion that took place after its initial formation. About 100 million years, a little less than 100 million years after the Earth formed, it merged with another planet called Theia. So our solar system actually began with 10 planets. Today it has only 8. What happened to one of those 10 planets is it merged with the Earth when the Earth was about 95 million years old. And that caused a lot more accretional heat to be built up in the Earth. But more than that, what happened is that Theia, being the smaller of the two bodies, there was a transfer of its heavy element material into the interior of the Earth, and the light element material got blasted out, and that's our moon. So this led to the formation of the moon. If it wasn't for this event, we wouldn't have our moon. But the moon has a lighter composition than we see in the interior of the Earth. So it's one reason why we got additional accretional heat. It's also another reason why we got an extra load of uranium and thorium. We got a question back there? Yes.
Hugh, I'm not a physicist, but it seems to me that as the early solar system, when the sun was there but there were no planets and everything was swirling around ready to accrete into the planets, it all would have been mixed up and be of similar material. And yet when it accreted out to the planets are all incredibly different from each other.
Yes.
What accounts for that?
Okay. Well, there's a temperature drop-off as you go from the sun to the outer part of the solar system. And so when you get past what's called the snow line, that being the distance from the sun where gases are going to be frozen, this is where you get the gas giant planets forming. Now, when you're interior to the snow line, those light gases will not freeze, which means they're not going to be collected. And so that explains why you get rocky planets interior to the snow line, and you get gas giants exterior to the snow line. Now, in the case of our solar system, it's a little more complex than that, because there was a grand tack phenomena where the gas giant planets moved towards the sun, stopped, and moved back. And so this kind of changes the formation history of what happened. And actually, that grand tack movement caused one of the gas giant planets to be ejected. So we actually had 5 gas giant planets. We got 4 today. But if it wasn't for that, for example, we wouldn't have Mars the way it is. Mars is an anomaly. Planet formation models basically predict the rocky planets will get bigger and bigger as you move from the sun out towards the outer part of the solar system. Mars should be the biggest of the planets. It's not. But it's because of this grand tack phenomena that we get a small Mars and not a big Mars. And but going back to this explains where Earth got extra accretional heat and also extra radiogenic heat. But that's not the only thing that happened. This grand tack movement actually caused a huge, because what happened as the gas giant planets moved in, stopped, and moved out, it destabilized our asteroid and comet belts. Our asteroid and comet belts were about 1,000 times bigger than they are today. And it was this movement of the gas giant planets that destabilized that. So much later than 95 million years after the formation, we're literally talking about 700 million years later, we get what's called the late heavy bombardment. So this movement of the gas giant planets destabilized the asteroid and comet belts, and caused the inner solar system to be bombarded by asteroids and comets. So, yes, right here.
If you don't mind, if you could go back to that previous slide.
Sure.
Okay, when I look at that, well, first of all, I read in your books that it was a 45-degree angle that this planet collided with the early Earth, right?
Yeah, so this
Okay.
figure is not quite accurate.
So it's not the scale, and I kind of envision it based on that picture that it collided at a fairly high rate of speed.
It actually was a fairly low rate of speed.
Okay.
If it was a
So
high
then-
rate of speed, it would have destroyed the Earth.
Right.
And so it was,
But think-
the collision was not head-on, it was at an angle, and it was a low-velocity collision, which basically caused this smaller planet to merge with the primordial Earth, but in such a way that the Earth's interior got super endowed with the heavy element material from the collider, and the light element material got blasted out, and that led to the formation of the moon.
So like the middle of the planet was injected with this planet kind of in a slow manner, geologically speaking.
Well, the merger event would have caused both bodies to become molten, but as the Earth began to cool from that event, there was a movement of heavy element material
Yeah.
into the core.
So it wouldn't have bounced off or anything
No,
like
it
that.
was no bounce off thing. Although I've written articles on this on our reasons.org website, because this actually caused some concern in the scientific community, saying, you know, this merger event, in order to get the moon to come out the way it is, requires extraordinary fine-tuning. And so a group of moon-forming researchers said, we need to redo all of our models, make them more detailed, and see if we can eliminate all this fine-tuning design that was in the original models. Well, they did that and discovered that the fine-tuning design went up instead of down, and also recognized that if it wasn't that precisely fine-tuned, the moon wouldn't be the way it is, and if the moon isn't the way it is, we human beings couldn't exist on the Earth. I mean, what's unique about our moon, compared to the mass of our planet, it's 50 times more massive than any other known moon. But that's because our moon formed in a way no other moon formed. But if it wasn't for that high ratio of the moon's mass to the Earth's mass, our rotation axis would not be stable. The reason why Mars's rotation axis flips back and forth by 60 degrees, it doesn't have a single gigantic moon closely orbiting it. Earth is the only planet in the solar system that has a stable rotation axis, and it's because of the moon. If the moon wasn't there, we wouldn't have that, and advanced life wouldn't be possible on the Earth. By the way, a British journal, Nature, commissioned all these origin of life researchers, or origin of the moon researchers, to redo their models to see if they could eliminate at least some of this fine-tuning design. As I said, they wound up concluding way more design. And a guy by the name of Tom Elliott wrote a little commentary piece in Nature where he said all this extra fine-tuning design is causing all of us philosophical disquiet. Philosophical disquiet because there was really no naturalistic way to make this work. So again, a testimony that God was involved. I saw a question somewhere here in the microphone. Yeah, right here, we can get a microphone. And by the way, please wait for the microphone. That way the people who are live streaming can hear your question.
Was this this Athena, did you call it?
Yeah, the planet that collided with the Earth or merged with the Earth has been given a name.
Okay.
They call it Theia.
Okay, Athena.
Theia.
Was this collision, was this was this part of that grand tack that you were talking about?
No, this was earlier than the
Earlier
Grand
than that,
Tack.
okay.
We're talking 95 million years after the Earth's formation.
Okay.
This particular event, the late heavy bombardment, happened when the Earth was about 700 million years old.
Okay, so
This
this is the grand tack right here? This showing
Well, the
that?
Grand Tack would be a cause for this event.
Okay.
Okay, but the Grand Tack actually took more time, which you see here, but it led to an extremely heavy bombardment of the Earth, And it also caused the interior of the Earth to be injected, not only with heavy element material, but also some extra oxygen and sulfur, and actually explains why our interior is the way it is. And just to put this in a time frame, the origin of life on planet Earth happens immediately after the late heavy bombardment. The late heavy bombardment would have liquefied the surface of the Earth, would have evaporated our oceans. It took 40 million years to cool so that the water would return, and you'd have rocks on the Earth that would be stable for the first time. However, in those rocks, they find the evidence for life, basically telling us the origin of life happened on planet Earth instantaneously. The moment the conditions would permit the existence of life, life is there right away, and it's there in great abundance and also great diversity. Now, we're only talking microbes, but we're talking a huge ecology of distinct microbial life forms, including photosynthetic life. This is when our atmosphere begins to be injected with oxygen.
One more quick question.
One more quick question, then we'll move on. Yes, where's the quick
You
question?
talked about
Yes.
the moon being, the mass of the moon being 50 times greater than that of the Earth?
I'm saying the ratio of the moon's mass to the Earth's mass is 50 times greater than any other moon-planet ratio of
Okay.
mass that we see. So, for example, we have moons orbiting Jupiter that are as big as our moon. But then Jupiter is 317 times more massive than the Earth. So yes, there are bigger moons, but if you compare the mass of our moon to the mass of its host planet, it's the supergiant of the universe. But only because of that do we have a stable rotation axis. And incidentally, that also explains why we have a 24-hour rotation period. The moon is close enough and massive enough to the Earth that it slows down our rotation rate. By the way, one of the things physicists do every New Year's Day, they alter their clocks. Because in 2020, the Earth is going to rotate slightly more slowly than it did in 2019. We're talking fractions of a microsecond, but it adds up over years. And it was such that when the moon formed, our rotation rate was like 2 or 3 hours a day, and that would not have been pleasant for advanced life. And so 24 hours is optimal for human civilization, and it's thanks to the moon that we have that optimal rotation rate at the best possible time in the history of the sun. One of the reasons why we can exist here. But moving on here, yes. Okay, moving on. If you got a question, let me know. One of the things we've discovered, and this is something you'll see in my book Improbable Planet, is actually looking at the abundance of elements in our galaxy and in our universe, and contrasting that with the abundance of elements we see in the Earth. Now, I purposely made these relative to iron and magnesium. I mean, what you'll see if you were to Google the abundance of elements is they make it relative to hydrogen, but that doesn't work for rocky planets. Because if you've got hydrogen and helium in the atmosphere of the Earth, our gravity isn't strong enough to hang on to that. So rather than making it relative to hydrogen, I've made it relative to iron and magnesium. We chose those because nuclear fusion in stars basically is a process of converting hydrogen into helium and then the helium into iron and magnesium. But as we compare the abundance of elements heavier than helium in our Earth with the abundance of elements heavier than helium in the rest of the universe in our Milky Way galaxy, we find that Earth is anomalous in almost every single heavy element. And the ones that are most spectacularly anomalous are these: potassium. Our planet Earth has 90 times as much potassium as what we would expect in other rocky planets. And as you're probably well aware, potassium is a life essential element. Your body has a lot of potassium in it. But when we look at another heavy element, uranium, it's 340 times more abundant. And then thorium is 610 times more abundant. Okay, so we are the potassium champion of the universe by a wide margin. Even more so, we're the uranium and thorium champions of the universe. Now, potassium is essential for life, but we now recognize that all three of these elements are radioactive. Yes, the potassium in your body is a radioactive element. That's one of the reasons why you can't live for millions of years, because your body's got potassium in it. Now, the half-lives of the radiogenic isotopes of potassium, uranium, and thorium are as follows. Potassium, most of it's potassium-40, decays into argon-40 with a half-life of 1.25 billion years. So that's what's happening to the potassium in your body. It's decaying, but it's decaying with a very long half-life, and because the half-life is so long, typically you don't die from potassium decay. So few potassium atoms will decay in your body, it doesn't really make any difference. Uranium, there are several radioisotopes of uranium. The two that have the longest half-life are uranium-235 with a half-life of 704 million years. And uranium-235 is the stuff you make atomic weapons with because it will undergo natural fission. And then you got uranium-238, which has a half-life of 4.468 billion years. And then thorium-232, it's 14.05 billion years. So the half-life of thorium is roughly the age of the universe. Now, it's thanks to our planet being so super endowed with potassium, uranium, and thorium that we have strong internal heat flow in the interior of the Earth, which explains why we have plate tectonics and a magnetic field, why we can recycle the life nutrients. And I've created a graph here which basically shows you, and incidentally, about 35% of the internal heat flow that we have in our planet comes from accretional heat. So that moon forming event, the late heavy bombardment, the formation of the Earth from planetesimals, that's about 30% to 35% of the total heat flow from the interior of the Earth. The 60 to 65% comes from these four radioisotopes. And I created this little graph here which shows you the degree to which the radiometric decay of these four isotopes contributes to the interior heat flow of the Earth. And so when the Earth is young, the dominant one will come from the short half-life. So potassium-40 and uranium-235, because of their shorter half-life, dominates the radiogenic heat flow in the interior of the Earth when the Earth is young. But most of the potassium-40 that the Earth had when it formed is now decayed away, so there's not nearly as much of it as there was. I mean, we're talking about 1/16 the amount of potassium that was there in the beginning. That much of it is decayed away. And so what you see is that just in the last few tens of millions of years, thorium has become the dominant contributor to the heat flow of the Earth. It superseded uranium-238 a few tens of millions of years ago. And then that dotted line there basically shows you the total heat contribution from the radiometric decay of these four isotopes. By the way, when the Earth was extremely young, less than, say, 200 million years old, then the dominant heat flow came from radioisotopes that have half-lives of only millions of years. Things like aluminum-26, neptunium. Beyond uranium, you got neptunium and plutonium. And so neptunium and plutonium dominated the heat flow when the Earth was less than 200 million years old. Today, the Earth has no neptunium at all, no plutonium at all. It's completely decayed away because the half-lives are only millions of years. All we got left today is the potassium-40, uranium-235, uranium-238, and thorium-232. Now, what's different about the Earth is that we've been able to retain this strong heat flow for over 4 billion years. And again, papers have been published saying we're likely to be the only planet in the universe that has been able to sustain strong internal heat flow for billions of years. And a little bit of physics history. The famous British physicist Lord Thomson came up with a calculation where he assumed that the heat flow from the interior of the Earth came 100% from accretional heat. Now this is before we knew about radioactivity, because he was writing this in the 1900s, and this is before they knew about the moon forming event and the late heavy bombardment. And so he said if it comes from that, and if the heat flow is conductive from the core to the interior of the Earth cannot be any older than 98 million years. Now, what you'll see in physics textbooks today is the big mistake that Lord Thomson made is he was not aware of the contribution from these radioisotopes. But you just heard me point out, that's still at most only 65% of the heat flow. The biggest mistake he made was he presumed that the heat flow was by conduction only. And as this graph here shows you, that's not the case. The dominant transport of heat in the interior of the Earth is not conduction, it's convection. And when you have convection, you've got the circulation of heat rather than the one-way flow of heat, and so this allows the heat flow to be sustained for 10 to 100 times longer than what Thomson had calculated. So by the way, when you read your freshman textbook book about where Lord Thomson was wrong, those textbooks are wrong. It's not the radiogenic, that is part of it, but the dominant factor was he ignored the convection mechanisms. Now, the little arrow you see there indicates where you got conduction. The solid core, because it's solid and made up of ferrous elements, indeed, it's almost 100% conduction. But once you get into the liquid core, it's totally dominated by convection, likewise throughout the mantle, and then when you get to the crust of the Earth, you've got something called advection. That's just a technical term meaning you've got volcanoes that are basically allowing heat to be transmitted from the mantle to the surface of the Earth. But yeah, the convection along with the increased accretional heat plus the increased radiogenic heat explains why Earth is unique in being able to sustain strong internal heat flow for billions of years. Now, one of the things I want to point out is that thorium 610 times more abundant than what we would expect in any other rocky planet. And if it wasn't for thorium being so super abundant, going back to here, it wouldn't be the dominant heat flow today. As a matter of fact, if we didn't have all that thorium, 610 times as much as what we see in other rocky planets, chances are plate tectonics today would have been shut down. Our magnetic field would have been shut down. There simply wouldn't be enough heat, because right now we're barely at the heat flow necessary to sustain the strong magnetic field and to sustain the plate tectonic activity. In fact, as we project hundreds of millions of years in the future, maybe only tens of millions of years, it's going to shut down. So that's something you might want to take into account in your investment strategies, is you need to realize a time will come when the magnetic field won't be here any longer. And we're not talking a lot of time on an astronomical time scale, literally just tens of millions of years, our magnetic field is going to shut down. Plate tectonics will shut down simply because the heat flow from the interior Earth will not be adequate. But if it wasn't for that huge abundance of thorium-232, that would have already happened. So one of the things you can go away with today is just to thank God for blessing our planet with such a huge quantity of thorium that we still have a magnetic field and we still have plate tectonics. Now, yes?
Okay, so in the case of this thorium-232, I assume because it has a half-life of nearly the age of the universe that it
Yes.
pre-existed Earth. And I guess my question is, a lot of these elements today they were like injected into the earth, or these isotopes or whatever they are, or did they actually kind of chemically develop? I don't know if I'm using the right terminology, but
No, I think I got you. 100% of the thorium in the universe, thorium and uranium in the universe, comes from supernova eruptions. And so I don't have the chart here, but this is a good piece of advice I'm getting from you. I think I need to add one more graph, which basically shows you the supernova eruption history of the universe. Supernova are giant stars. If a star is bigger than a certain mass, it will end its burning cycle with this super nuclear reaction, and it basically causes the star to explode, and the nuclear reaction produces a lot of elements heavier than iron, including lots and lots of uranium and thorium. And so there's a graph I could show you, but I don't have it here, basically showing you the frequency of supernova eruptions with respect to the history of the universe and the production of uranium and thorium. Now, what's complicated about this is supernova make uranium and thorium, but uranium and thorium are radioactive, and so they decay. And so once uranium and thorium has been produced, it will start to decline. But if you put the two calculations together, you basically can develop a graph of the abundance of uranium and thorium in the universe with respect to the age of the universe. And it is such that you get a maximum amount of uranium and thorium when the universe is about 9 billion years old. Okay, when did the Earth form in the history of the universe? It formed when the universe was 9 billion years old. So one of the reasons why we're so super endowed with uranium and thorium, our planet formed at the time when the universe was at its maximum uranium and thorium enrichment. And again, because of the star cluster in which we were formed, we got saturated by nearby supernova eruptions. And incidentally, that must be fine-tuned. If our emerging solar system was too close to one of those supernova eruptions, our solar system would have been destroyed. But if it's too far away, we wouldn't have been injected with sufficient quantities of uranium and thorium. So I'm basically telling you it's nothing short of a miracle that we got 610 times as much thorium as what we would see in other rocky planets. And it's because of that we actually still have our magnetic field and still have plate tectonics. Okay, quick point here. Why do we need a strong magnetic field? We need it because that sets up a magnetic belt around the Earth that protects us from deadly solar radiation and deadly cosmic rays. Also, it prevents the solar radiation from sputtering away our atmosphere and evaporating all of our oceans. So if it wasn't for the fact that we had this strong magnetic field for 4 billion years plus, our oceans would be gone and our atmosphere would be gone, and life would be radiated by these deadly cosmic rays and solar particles. So it's something else you can go away with today, is being grateful for God setting up all this thorium so we can still have a magnetic field that means that we get shielded from these deadly cosmic rays and solar particles, and our water remains stable on the Earth as well as our atmosphere. As for the plate tectonics, it takes the plate tectonics actually to build continents. Our planet started off as a water world, where there was only ocean on the surface of the Earth, and it's thanks to the plates sitting on top of this soft mantle where they're able to move against one another thanks to the convection flow in the mantle, which caused these plates to move against one another, that you actually have oceanic plates that slide under the silicate plates. And it's that movement that actually makes the silicate. So Earth's crust started off as nothing but basalts, but thanks to plate tectonic activity, some of those basalts got converted to silicates. Silicates are lighter than basalts, so actually as you build up enough silicates, it causes it to break the level of the oceans, and you get surface continents. And it's thanks to the fact that we have a planet with surface continents and surface oceans, that you get a cycle whereby these exposed silicates have rain falling on them. You need a water cycle. It's crucial you have a water cycle, so you've got rain falling on these silicate exposed continental land masses, which sets up a chemical reaction that I showed you 2 weeks ago. Hope you all remember it, that if you get water falling on silicates, the water acts as a catalyst to convert the silicates into carbonates and sand. Don't take sand for granted. If it wasn't for the plate tectonic activity, we wouldn't have sand on planet Earth. We wouldn't have carbonates. And if you don't have carbonates and sand, you're not going to have concrete for your freeways or concrete for your skyscrapers. So that's one of the reasons why we can have the civilization that we do. Get the microphone over here. But let me just say this before I take your question. The big benefit for long-term survival of life on planet Earth, rain falling on the exposed silicates not only makes sand and carbonates, it pulls carbon dioxide out of the atmosphere. So as the sun gets brighter and brighter over its history, the sun today is about 22% brighter than it was when life first appeared on planet Earth. But because the silicate cycle was taking carbon dioxide out of the atmosphere, as the sun got brighter and brighter, our atmosphere got progressively less and less efficient in its capacity to trap heat, keeping the temperature at the surface of the Earth optimal for life for the past 3.8 billion years. And if it wasn't for 3.8 billion years of life history in the Earth, there wouldn't be human beings and there wouldn't be human civilization. Let's take your question.
Well, you beat me to the punch here a little bit.
Oh, sorry.
About the temperature of the surface, the crust. I mean, there's certainly a large temperature gradient between the center of the Earth and our crust. And I'm wondering what would be the magnitude of the solar heat source, solar radiation at the surface, say compared to this internal heat flow. And in terms, I mean, there's so many variables here in terms of doing any kind of a heat transfer modeling. Early on, you got a fast rotation rate, so much more convective heat transfer.
Yeah, I can
to the
answer your
surface.
question. If you're
So-
talking the surface of the Earth,
Yeah.
the solar heat is 99.97%.
How
The
about
heat
compa-
flow from the interior is only 0.03%.
Oh, okay.
So you can basically, if you're talking the surface of the Earth, you can ignore the heat flow from the interior of the Earth in terms of what the weather is going to be like tomorrow. It's not going to make any difference. However, where it does make a difference, go down just a few tens of meters into the crust, and now the heat flow from the interior of the Earth dominates the solar radiation, because the solar radiation doesn't penetrate very far.
Right.
So we're talking the surface, yeah, you can ignore the internal heat flow. The heat from the sun is the totally dominant factor.
Okay.
But once you get a little bit below the surface, the heat flow from the interior becomes dominant.
So the global warming model algorithm guys don't have to put this in their models.
Yeah, I mean, 0.03% isn't going to make enough difference. The errors they have in their models are larger than that.
Yes.
Maybe a time will come where that makes a significant difference. What we do know that it could have an impact is that you get more heat flow under the continents than you get under the basalts. And that's just because the silicates, again, are lighter, and so it permits a faster heat flow than what you get through the basaltic, the ocean basalts. So yeah, it depends what kind of tectonic plate you're sitting over. And different tectonic plates are thicker. Some are thicker than others. And so there will be some differences as you go over the surface of the Earth.
Now,
But,
where in that time period would you put the 7,000 parts per million of CO2 that occurred? I remember that was in your book, Improbable Planet. I forget when that was.
Yeah,
100
no,
million?
where we got a good history of the amount of carbon dioxide in the atmosphere is from the origin of life onward. I mean, one way we can get a handle on what the carbon dioxide quantity in the atmosphere is looking at what kind of life existed in the Earth at that time. And so, yeah, if you go back to the origin of life, I think it was like 70,000 parts per million, and today we're looking at about 400 parts per million, although during the last ice age, it got down to 165 parts per million. So that's the lowest it's ever been in the history of the Earth, was what happened during the last ice age. One of the concerns with the ice age models is that the next ice age could actually drop the carbon dioxide level below where it was in the last ice age. That's a concern, because once the carbon dioxide level drops down to 150, photosynthesis stops. And so photosynthesis, one reason why humans during the last ice age were not able to launch the kind of civilization we see today, there simply wasn't the carbon dioxide in the atmosphere to support the plant productivity that we have today. So all that'll be in this book of Weathering Climate Change. But I wanted to say a little bit about thorium. I mean, one of the things I barely discussed in this book, Weathering Climate Change, was how thorium could actually help us stabilize the climate, in the sense that, any of you have heard about global warming and climate changes. We have to somehow shift our dependence for electricity and power away from fossil fuels to energy sources that don't pump greenhouse gases into the atmosphere. And nuclear power is one way to do that. We got another question over here? Yes.
Real quick, you mentioned the weathering of the rocks, pulling out the CO2 from the atmosphere. Is that a significant, considered negative feedback for the warming as much? So we're going to get more heat, more vapor content, it's going to be more rain, but it needs to be over the exposed rocks. Is that correct? Is that something that they're considering?
Well, it's a little more complex than that, because it's the surface area, the silicates, that are exposed to rainfall that determines how much carbon dioxide is pulled out of the atmosphere.
So not the amount of rain.
Not the amount of rain. It's how much of the rain gets onto the exposed silicates.
I see. So there needs to be mountain ranges and so exposed rocks.
Yeah, mountain ranges, you're going to have greater exposure than flat plains, because you get more surface area being exposed to the rain. And actually what you see over the 3.8 billion year history of life on planet Earth is that that rate of removal has been accelerating. And that's important because of what's happening to the physics of the sun. It's important that it accelerates. And what's responsible for the acceleration is the history of life. One reason why the history of life looks the way it does is that over time, life becomes more capable of breaking up the silicates. I mean, another slide I could put in here, I've got it, but this is actually helping me in developing this talk, is to show a slide basically of a silicate mountain that's covered by conifer trees. And that's the amazing thing about, you see this all over the Sierra Mountains in California. We got these conifers, these trees, that grow in granite. And you say, that's one of the amazing things about these trees, is they can germinate and grow in pure granite. And what happens is these trees basically send out powerful roots that break up the silicates, but by the way they break it up with their powerful root system, it allows rain to penetrate deep into the silicates. And so instead of just the surface part of the silicates being exposed by rain, the interior of the silicates gets exposed. And it's been calculated that the creation of conifers 350 million years ago actually accelerated the drawdown of carbon dioxide of the atmosphere by about a factor of 4 times. So actually life plays the crucial role in regulating the rate at which, and that's one of the challenges we give to the evolutionary paradigm. Only a God with a mind that knows the future physics of the sun is going to know what kinds of plants to create on Earth at what time and what abundance in order to pull just the right amount of greenhouse gases of the atmosphere to perfectly compensate for the brightening of the sun so life can remain abundant on the surface of the Earth. If there's no mind behind this, you're going to get out of sync. And if you get out of sync, the planet becomes permanently sterile. And clearly that did not happen. Okay.
Hugh?
Yes.
One more online over here.
Okay, got an online question?
Actually, it's my question, but I
I have to ask it and then leave. Do you think that it was God's goal for people to create modern technology and civilization as it is today? I ask because I think many people in our culture basically think we should have stayed in the Dark Ages, or I mean, well, anyway, yeah, not
Well-
the Dark Ages, but in a.
No, I'm especially seeing that with this,
And-
climate change controversy.
Right.
Is the way we need to deal with this and stabilize the climate. We need to drastically lower our population, and we need to survive with all this high technology.
But
Yes.
also, if I may, also, how does that work in with the ideas of manifest destiny? And how,
Well, let me suggest a different kind of manifest destiny. I mean, what I notice as I go through the Bible's major creation texts, every single one of them links the doctrine of creation with the doctrine of redemption. In fact, there are passages in this book that tell us that God begins his works of redemption before he creates anything. So before God created the universe, he already began to put in motion his works of redemption. A couple examples would be 2 Timothy 1:9. The grace of God that we now experience was put into effect before God created time, before the beginning of time. The hope that we share in Christ was given to us before the beginning of time. Now, one of my responses to people is say, well, maybe the way we need to solve this global warming problem and climate change is bring our population below 1 billion. And, let's just sacrifice our technology, get rid of our cell phones, get rid of our cars, get rid of our factories, and then we'll have a nice, stable climate. It's ignoring the fact that from a biblical perspective, God wants to redeem billions of human beings. Not just millions, but billions. After all, he's got a new creation, and he's told us in the Bible that he's going to need a lot of us to basically take on all the jobs that we're going to have in the new creation. We're going to be teaching the angels, we're going to be ruling over what God creates there, and he's going to need a lot of us to do that. And so he wants billions. And so lowering our population below 1 billion is not in the cards from a biblical perspective. Moreover, we're told in the Bible that the role of God's people is to take the good news of redemption to all the people groups of the world. That requires technology. I mean, one member of this class years ago, before he passed away, was, I can't think of his name. He was a missiologist at Fuller Seminary. Ralph Winter, thank you. Ralph was in this class, and he actually wrote several research papers before he passed, making the point that today evangelical Christians have the technology, the people numbers, and the wealth to take the good news of salvation to all the people groups of the world in less than 10 years. He says all we lack is the motivation. And today I would say that number needs to be corrected. We could do it in less than 5 years. But my point is, we need technology. And God wanted billions to be redeemed, not just millions. Now, addressing that very point, notice that God intervened in such a way in the history of the earth, we got 610 times as much thorium as what we would expect in any other rocky planet. Could it be we're overlooking a special gift that God gave us? Yes, that thorium explains why we got a magnetic field. It explains why we have this plate tectonics existing today. But it also is a means by which we could get all the energy we need at a rate that, literally, we could get 100% of our energy made from thorium reactors. Okay. Is there such a thing?
You?
Yes. Back here.
Yeah. What book in the Bible says billions?
What book of the Bible says billions?
Yeah.
Okay. Revelation, chapter 7, where the John the Apostle basically makes the point that he saw a vision of the redeemed hosts. And he said this, it's chapter, verse 1 and 2, there's redeemed hosts standing before God, worshiping God, from every tribe, nation, language, people. which I believe is a reference to the fulfillment of God's redemptive plan. And what does he say? It was an uncountable number. Now, the Greeks in the first century, and John was writing in Greek in the first century. At that time, they had a number system that took them up into the billions. So basically, when he's saying an uncountable number, he's talking something in excess of 1 billion, probably several billion people. So that's where I would get that from. And one thing you do see in the Bible in terms of numbers is the phrase that there was a myriad of angels. That's 10,000 times 10,000. So that's the biggest number you see in the Bible, 100 million. But it talks about myriads and myriads, which means several hundred million. And again, the Greeks used this system to get up to 1 billion plus. And so that's where I believe we can discern that God wants to have billions redeemed, not just millions. Okay, we can get a microphone over to this young lady here. No, we want this to... I know you got a loud voice, but still, go ahead.
Okay.
Because we're recording this.
Why did Jesus then say, narrow is the way and few are entering?
Okay, good question. Why did God say narrow is the way to salvation and broad is the way to destruction, if indeed he's going to be redeeming billions? Okay, one of the things you'll see in my book, Improbable Planet, is a table that shows you the number of human beings that have lived since God created Adam and Eve. Conservatively, it's 130 billion people. Okay, if God redeems, say, and by the way, if you look at Zechariah, chapters 11 and 12, tell us a day will come when 1/3 of all Jews in the world will be followers of the one that they have pierced, a reference to Jesus of Nazareth. So it's referring to a future conversion of the Jews. It says, narrow is the way, but given that number there, and given the fact that the Lord hasn't returned, I mean, conservatively, the number of people committed to bringing people to faith in Christ in the Christian community, we're looking at north of 15% of the world's population. So 15% times 130 billion is tens of billions of people. And he hasn't come yet. Maybe the percentage is higher. Maybe the percentage is as high as what it's going to be with the Jews, where it says 1/3. If it's 1/3, we're looking at about 40 billion people being redeemed. That's one reason why I believe that the new creation is not going to be on this planet. This planet is simply not big enough for 40 billion human beings. So it's going to be a new earth. And if you read Revelation 21, the new earth is gigantic compared to the present earth. So that's another reason why I would say we're looking at a large number of people be redeemed. Yes, it will not be a majority, but it's going to be a significant minority, significant enough we're looking at tens of billions of humans will be redeemed, which means we're going to need to have billions of people on the face of the earth today. Okay, let me try to move into, I think something that's been overlooked by people who are concerned about climate change and global warming, and that is the potential of thorium nuclear power. And incidentally, this is the first thorium reactor ever built. It was built in 1962 on the Hudson River in New York, Buchanan, New York, Indian Point Energy Center. It's still there. And it was basically a pilot project. Let's see if we can make this work. And they were able to prove, yeah, this really works. It does generate energy. But it was never pursued. It's now being considered because of the concern about climate change and global warming. But it's been basically mothballed since 1962. You say, why has it been mothballed? Well, one of the disadvantages of thorium power generation, you can't use it to make weapons. But that's now considered to be an advantage. In other words, we could export these thorium reactors all over the world without having any risk that they're going to be used for terrorist purposes or to make bombs. Because it's not like uranium. You really can't make bombs out of it. Now, here are some considerations about thorium nuclear power. Because our planet was so super endowed with thorium, there's 3 times as much of it as there is uranium. And 1 ton of thorium produces the energy equivalent of 200 tons of uranium. So you literally get 200 times the energy generation from a ton of thorium than you get from uranium. And guess what? There's 3 times as much of it available in the crust of the earth. Or to compare it to coal or gasoline, fossil fuel burning, 1 ton equals 3,500,000 tons. So I mean, here's all this alarm going on today. We have to stop burning fossil fuels. Well, look at this. 1 ton of thorium replaces 3,500,000 tons of coal or oil or natural gas. Now, as far as the United States, we have the 3rd largest reservoir of thorium on the planet. Australia and India are slightly ahead of us, but there's enough thorium in the United States to produce 100% of the U.S. total power needs for over 1,000 years. Now, that's just the proven reserves, the stuff that's easy to mine. Okay? There's probably a lot more thorium. There's thorium in Canada and Mexico as well. Now, in terms, everybody's worried about the radioactive waste you get from nuclear power. With thorium, you get 1,000 times less radioactive waste. Moreover, the waste that you generate is safe to handle after just 200 years. Now, if you're talking uranium, it's safe to handle after 10,000 to 100,000 years. And it's much more dangerous than what you get from thorium. So the radioactive waste issue is a lot more manageable with thorium by orders of magnitude than it is with uranium. Now, it's safer and more efficient to mine than uranium. I mean, when you're mining uranium ores, you really have to go to considerable expense to protect the miners. That's not the case with thorium. It's safe to mine, and it's much cheaper to mine. You basically can mine it through open pit mining, which you can't do with uranium. With uranium, you got to go underground, and you got to create a vapor. It's quite expensive, and so there's 3 times as much thorium, but it's also really cheap and efficient to mine. And then we're always worried about meltdowns of nuclear reactors. With thorium reactors, there's a 0 meltdown risk. It's easy to make a reactor whereby any threat like that, it immediately shuts down. And so we can guarantee to the public there will be no meltdown risks with thorium reactors. And as I mentioned before, one of the now considered to be advantages, this used to be a disadvantage back in the 1960s, but now is considered to be an advantage. The thorium reactor production cannot be diverted to make nuclear weapons or to make terrorist weapons, which means there's no risk of having all the nations of the world, regardless of whether they're rogue nations or not, using this to generate power. Now, this is a bit of an overstatement. If you use extremely high technology and a whole lot of money, there is a way to make a weapon out of a thorium reactor. Basically use the thorium-232 to make uranium-233. The problem is, when you try to make a nuclear weapon out of uranium-233, the chances of killing the people who make the weapon are very high. And so the people are trying to, and then moreover, it's dangerous to use, and you never, and it can explode at a whim. So it's like anybody in their right mind is not going to want to go down the route of uranium-233 weaponry. But just to be clear, it is a way that would work, but no one's ever going to do it because of the risks to making it. And if you got a thorium reactor, you really don't have to worry about the thorium plant workers. The radiation exposure is going to be minimal, and you're not going to have to worry about them doing something stupid. They're going to be safe. And to me, what I think is impressive, it takes only a decade. If we were to make a decision today We're going to go with thorium nuclear power plants all over North America and the world. How much time would we need to actually have 100% of our power come from thorium and no other source? It could be done in 10 years. Matter of fact, a group of nuclear physicists made the point with this reactor back in 1962. If we made a decision in the 60s to go to thorium, by the year 2000, the world could have been 100% getting all of its power from thorium reaction. But now we got more advanced technology. It literally could be done in 10 years. We got a question over here.
A number of years ago, maybe 10 to 15 years ago, Professor Nathan Lewis at Caltech, he's been lecturing about this for a long time, about the alternative energies
Right.
and so
Yeah,
on.
he's well known for doing this.
And he said that we would need to be building like a nuclear plant every day for a long time to meet global energy demands. So how does that square with what you've said?
Well, there are some negatives to thorium. I mean, one negative I already mentioned, you can't use it to make weaponry. A second problem is it's more expensive to build a thorium nuclear power plant than a uranium nuclear power plant. So the startup cost is higher. However, the payoff is much higher. You get way more energy out. And so it would take, now when I say it would take a decade, that would mean you would need a really concerted effort and basically a consensus that this is the way to go, everybody agrees with, there's no political battle, and we're going to spend the money to make these things happen. And basically looking at the fact that once this is in place, we're going to be saving a whole lot of money and energy. I mean, that's how you sell it. You basically say, hey, what if you didn't have to spend money on fossil fuels anymore? And what if you had all the electricity you wanted for 1/20th the price of what Southern California Edison charges you today? That's how you would motivate people, but you've got to put up a lot of front costs. Okay, another thing that hasn't been considered is that back in the 60s, the US didn't have a big national debt. Okay, today we got an enormous national debt. So this is not possible for the government to jump in and say, we're going to make this happen. This is going to be done by private industry. And so you've got a big startup cost, and it's going to get time to make a power plant big enough that you're going to start making money. And that's one reason why we haven't seen private industry go down this path, is they said, well, I mean, we got to put this upfront money, and we have to scale up. And after all, this thing was just a small, I mean, you got to make something way bigger than this to make this work. Then you've got to find a way to distribute the energy. So, but what's making it easy today is that, we do have electric-powered vehicles that can run for a long time. And if this were to become a huge enough source of energy, we could actually replace all the filling stations with people where they can plug in, get their cars. And actually, you could have them recharge their cars at 2,000 volts instead of 220 volts, which means with the time it would take you to fill it up with gas, you've got enough electricity in your car to go for a week. So there are ways around this, but the upfront costs are not trivial. So that is a factor that needs to be considered. And I think the only way this is going to happen, and I already see this happening, nations in the world, Israel's involved in this, the US, China especially, Russia, they're all thinking down this direction, mainly because they're saying this is a much cheaper way to generate power than what we have right now. And so things are starting to happen, and I think this is going to be a good sequel to all the public concern over global warming and climate change. This is a way to go where everybody wins. We can stabilize the climate and we get energy at a much cheaper cost than what we're paying for today. And that's kind of what I wrote about in my book, Weathering Climate Change. The only way we're going to be able to stabilize the climate is to give people an economic motive to do so. Basically, in my book is the anti-Al Gore book. Al Gore was saying, we need to deal with this problem, and we need to sacrifice our technology and our income and our economy to make it happen. And basically, he's overlooking a biblical principle. We human beings are fundamentally selfish. Trying to convince everybody in the world to sacrifice their economic well-being is not going to be an easy sell. And if you sell it to some people, other people will cheat. And it's something I did with my son's friends. I gathered them all together and said, okay, you're all concerned about global warming and climate change. How about all of us agreeing that we're going to get rid of all of our technology, and instead of living on $50,000 a year, we're going to live on $8,000 a year. And they said, we'd rather see the whole earth go down in a pile of smoke than do that. So even with people as wealthy as they are in the United States, you're not going to get buy-in for that kind of an economic and technological sacrifice. On the other hand, what I shared with my sons and my sons' friends was this: would you be willing to stabilize the climate if it meant that it doubled your income? And they said, well, if it's going to double our income, yeah, we're all for it. And that's kind of what I'm doing in my book, Weathering Climate Change. And this thorium thing is one of the proposals, but it's not as well developed as what I shared with you today, is that there are ways that we can stabilize the climate. But by the way, what I am saying too, even then there's a limit. There's a limit to how long we can stabilize the climate. 1,000 years, 1,500 years, yes, but not 10,000 years. Eventually, the ice age cycle will take over, and then our climate stability will end. Yes. Let's get the microphone over to this gentleman.
I know we don't have too much time, but
We got 1,500 years.
yeah, I know. But within that 1,500 years, how do we dialogue with people that are Christian, that are young Earth, come from a young Earth Creation Research Institute point of view? How do we use the information that you gave us today to show that it takes a lot more time than just 7 literal days?
Well, it's interesting that within the Christian evangelical community, you've got a lot of climate change deniers, a lot of global warming deniers. And that's one thing I'd really tried to do in the early chapters of this book, is basically lay out the latest measurements that basically demonstrate, yes, the planet is getting warmer. And it's based on a new set of measurements that for the first time give us a detailed, indisputable temperature record for the past 9,500 years. Basically showing that there were natural cycles that were cooling the planet. If it wasn't for human activity, the global mean temperature today should be about 15 degrees centigrade colder than what it is. What was happening was that the natural cycles were cooling the planet, and still are cooling the planet, but at the same time, the advance of human activity was warming the planet. And for 9,500 years, they were perfectly compensating for one another. The amount that the natural cycles were cooling the planet were counterbalanced by the increase of human activity that was warming the planet. That's been sustained for 9,500 years, except the last 70 years. And actually, if you look at that temperature thing, what you notice, it took 8,700 years for the global mean temperature to cool by 1 degree centigrade. So human activity has not quite kept pace with the cooling that's been taking place, thanks to the orbit of the Earth about the Sun and what's happening to a rotation axis tilt. It cooled by 1 degree. In the last 70 years, human activity has accelerated to such a degree it's warmed by 1 degree, which means there's no need to panic. Right now, the global mean temperature is as warm as it was 8,700 years ago, and we were doing just fine 8,700 years ago. Where the alarmists are coming in is saying, but yeah, if it keeps going up by 1 degree every 70 years, then we're going to melt the polar ice cap, and when that happens, we're going to bring on an ice age. Things are going to get really bad. And all of that is correct. And so it would be well within our best self-interest to prevent the global mean temperature going up another 2 degrees centigrade. If it stays where it is right now, we're fine. And basically, there are economic steps that we can take that would work to stabilize the climate and at the same time boost the economy, not only of the wealthy nations of the world, but especially the poor nations of the world. And this is my motive. I want to take the politics out of this debate. The reason why there's politics, there are people saying, okay, we need to stabilize the climate, and you've got other politicians saying, but yeah, if we have to make that kind of an economic sacrifice, it's not going to work. If we make it a win-win, then I don't care what kind of politician you are, you're going to vote for it. And everybody else will vote for it too. But thorium, I think, is one of about 40 different things that we can pursue that actually increase the economic well-being of everybody in the world, at the same time stabilize the climate. And incidentally, this does not take into account that the energy demand of the world likely is to go way up. I mean, this set of numbers I've given you here assumes that people are going to be happy with expending the amount of energy they're expending now. But traditionally, that's not been the case. Energy demand has been going up exponentially, but one of the advantages of thorium nuclear power, you can increase the energy demands of the nations of the world and still has zero impact on the climate of the Earth. And so if we want to double the energy flow, we can do that. And incidentally, if you were to make electricity, say 5% of the cost of what it is right now, believe me, people will use more energy. They're going to find a lot more things they can do with cheap energy. But this is a long-term source. And let me close with this. I think one reason why we've not gone down the path of thorium nuclear power is because the physicists of the world, the nations of the world, have been enamored with fusion power. I remember when I was an undergraduate student in the 1960s, my physics professors were saying, hey, on this very campus that you're on, we've got a tokamak where we're working on building controlled fusion. And if you're not familiar with the term, it's basically copying the energy of the sun, where you take hydrogen and fuse it into helium, and you make enormous amounts of energy. And I remember my physics professors in the 1960s saying, you know, we're making such great advances in nuclear fusion. By the end of the century, everybody's going to be using nuclear fusion for energy production. Well, the year 2000 came by, there wasn't one fusion reactor operating in the world. Here we are in 2020. Do we have any fusion reactors operating in the world? The number is still 0. But there's still huge amounts of money being spent on fusion reaction because the promise is unlimited energy. Well, with thorium, it's not unlimited. There's only a limited amount of thorium we can mine from the crust of the Earth, but it's still a number that for all practical purposes would be unlimited. Huge amount of thorium, and basically this is a proven source of power. It's not something that's still stuck with huge scientific difficulties. The reason why nuclear fusion hasn't panned out, you have to find some magnetic bottle that can trap the hydrogen in sufficient densities that will fuse into helium. And one of the things we've learned over the past 60 years is that making small magnetic bottles that are very effective traps, looks like many physicists I know say it's impossible. The only way we can have a stable enough magnetic field is if we got a lot of gravity. It works for the sun because the sun's got a lot of gravity. But we're trying to make nuclear fusion without gravity, which means you got to do it 100% with a magnetic field, and we've not been able to find any technological way of making a strong enough and stable enough magnetic bottle to make this work. With thorium, that's not an issue. Okay.
You were out of time. And
I'm out of time.
Yeah, I just want to let everybody know that someone has kindly packaged some fruits, some looks like tangerines and oranges, or tangerines and lemons.
Oh yeah,
over
a
there.
whole pile of citrus
so
over
they're
there.
little bags. You can have them and take them with you. But with that, I let you close us in prayer, and we can
I'll do that. But hey, one of the blessings of this class is all the treats that people bring. And Father in heaven, we thank you that we live on a planet that is so abundant in the food that it produces. It's abundant in all the resources we need to fulfill our purpose here on Earth. It's especially abundant in thorium. And Father, thanks to all that thorium, we've got an atmosphere, we've got an ocean, We got an optimal temperature on the surface of the Earth. We've got a magnetic field that protects us from deadly radiation. And we got this plate tectonics that recycles all the nutrients we need and helps to compensate for the physics of the sun. Lord, we're so super endowed. And not just super endowed with thorium, but everything we need for our well-being and our civilization. Clearly you're a God that loves us. Clearly you're a God that is really wanting us to fulfill the purpose and destiny for which you created us. Thank you for giving us everything we need. And thank you, Lord, that we can do it in such a short period of time. Father in heaven, I pray that as we leave this room, those of us who are followers of Jesus Christ would take up your exhortation to take the good news of redemption through Jesus Christ to all the people groups of the world, so that one day, as beautiful and as abundant as this planet is, we can be taken to an even more superabundant location where evil and suffering will never exist again, and love will be manifest throughout all of your kingdom without limit. In Jesus' name, amen. Thank you.
You know, I'm praying that we never get the ability to have a clean fusion, because that